Testing. I don't know where it works. Yeah. All right, let me have your attention. Let's start the class for today. And the official due date for the lab 1 was until last night. But I would like to extend the lab 1 due date for 1 more week, because like there were many students who requested me about like that they joined the class a little late, so need a little bit more time. But that means that like we will not have like a 75% due date for the lab 1, but I will accept all of your submission until next Monday as like the 100% due date. Yeah. Thank you. Yeah. I was not thinking that like they will be like welcomed like this. Yeah. But yeah. Please let me know if you have a lot of troubles in like the finishing the lab assignments, because like I know that this will take a lot of your time, but I would like to assist you as soon as possible. You realize the problem, so please be on Discord and then ask a lot of questions on it. Yeah. And then were there any issues on submitting the lab 1 assignments? Yes.
I just want to make sure that as long as it's on get back with the tag that final it's submitted.
So as long as you can see the tag lab 1 final on the drop-down menu on your like the commit tree kind of thing, yeah, then you'll be okay. And then make sure that your lab 1 final is correctly tagged on the right commit. Yeah. So then what I will do is like I will just check out your repository and then clone the repository and then check out on the lab 1 final and then run the grader on it. So that's the basic mechanism. So yeah, please make sure that you tagged on the right commit to for the thing that you want to get grade. So that's it. There's no email or other submissions. So what you need to do is like you need to commit and push. So that don't forget to do push, because like otherwise I cannot even see your commits. Yeah. So the rule is simple. So if you can see your commit with the tag lab something final on GitLab website, then you are fine. Yeah. And the next is about a little bit of recap about what we have learned about the protected mode. So in the real mode, we will use segment register as a multiply by 16 and then add the offset. That's how we calculate the address. But in the protected mode, we will refer to the global descriptor table. And then this global descriptor table stores 8-byte data. And then those 8-byte data will point some of the base address and then some of the limit address, and then it will contain a little bit of flags that we can honor for like a memory permissions or memory limit granularity kind of thing. Yeah. So one of the importance about the granularity bit is that like if we set the G bit as 1, then it will regard the limit address as a granularity of the 2 to the 12, so 4096. And the reason is we only have a 20 bits for the limit specifying the limit address, but by multiplying that by 2 to the 12, then we can point anywhere in the 32-bit space. So that's how the early stage engineers enabled the 32-bit full memory access using the segmentation. And another caveat in using segmentation is that like so the registers in CPU is somewhat scarce resource in the early days. So Intel engineers do not wish to spend additional registers to store the privilege level. So they hide the current privilege level in the CS register, because we will never use the last 3 bits of the CS register, because each of the segment selector will point to the start of the global descriptor table. And because the size of the global descriptor table is always multiplied by 8, yeah, so multiply of 8. So that's why like the last 3 bits are all 0, and we can hide our privilege bit in there. And there could be 4 levels available in the Intel CPU, 0 to 3, but we will only use 2 levels. So the one is a 0 for OS kernel, and then privilege level 3 is for the user application. Yeah, question?
So it says that you said that the last 3 bits aren't used and
Yes.
the last 2 are used for the permission level.
That's
What's
right.
that third bit for?
So the third bit is used for indicating whether to use a global descriptor table or a local descriptor table. But we don't go over the local descriptor table here because like we will not use that. So the only difference is like the global descriptor table is for the operating system and local descriptor table is for the application. But the interesting thing here is that like if we need to learn about the global descriptor table and protected mode because our booting sequence uses that, but we will not use local descriptor table. So not to have any kind of confusion, I don't even explain that in here. But you can regard that like the local descriptor table is using the segmentation memory model within the application. And then like we need to turn on the protected mode. And before turning on the protected mode, we need to set these kind of the global descriptor table. So what JOS does in their boot sequence is that like they set up the boot global descriptor table and then load it with the LGDT instruction and then turn on the protected mode by enabling the PE on bit, which is the rightmost bit of the protected the CR0 register, and by enabling that by 1, we can let the CPU know about like we enable the protected mode. And then to change the current privilege level, right after turning on the protected mode, to get into that mode, we need to run the long jump instruction with the specify the segment selector register. Any questions about the protected mode segmentation? So the most important part is that after enabling protected mode, it goes to the referring to the global descriptor table to get the base and the limit and the actual address translation. And next, we learned about a little bit about the virtual memory. And I introduces 3 goals of the virtual memory with the different examples. And these are transparency, efficiency, and protection. And the transparency, it refers to that like if we have a physical memory like this, suppose we want to load another program in the physical memory, then we need to think about what kind of programs we need to kick out from this physical memory and then like bring in the program in which address. We need to determine all of those. But the good thing about the virtual memory is that like we can give the full transparency of using address for the programmers. So what that means is that, so suppose we have 2 programs like this, then no matter what kind of the physical memory status we have, what we can offer is like the programs can use their own address. For example, program 1 and 2, these 2 programs are using the exactly same address space. What that means is that the program code will be residing at the 804.8000 to 800, and then the program 2's code also reside in that address. And then uses the same address for the stack. But even if the 2 programs are using the same address space, what we can do with the virtual memory, so that you can regard the virtual memory as like you will have an interaction table that writing all the virtual addresses on the left and then all the corresponding physical addresses on the right side. And if we have this table and the program itself, then we can translate any kind of the virtual address into physical address. So we conceptually see that this kind of the virtual address mapping, and then because virtual address is totally virtual to each of the process, then we could have a full transparency because like we can give any kind of address space to the program for use. And then for efficiency, the efficiency problem was like even if we have like some of the empty space, suppose like these yellow parts are empty space, then we can fit another program's required memory, but that needs to find some of the contiguous space are empty in the physical memory space. Otherwise, we cannot fit in that memory block. But by using the virtual memory, we will cut each of the memory into like the smallest unit called a page, and then we will later manage all the memory in the page size, page granularity, and that can actually remove the fragmentation issues. So efficiency problem could be handled by the virtual memory. Yeah, question?
So in that previous diagram,
Yes.
are those program code chunks pages?
So
Is that
like
what
the
it's representing?
it is actually the one chunk, but I depicted it in as 3 different blocks because it spans over 3 pages.
So it is pages.
Yes, so you can regard each block as a page, but the program code can be like the bigger than 1 page size, or it could be 100 pages, and like we can choose whatever page is available on the physical memory side. Yeah. And then the next is about the protection. And then how we can get the protection is that like what we want is like suppose program 2 uses stack at here, but if this stack goes underflow, then it may touch like program code part, or if it goes far down there, then it could also affect on the another program's stack. And to prevent that, what we can do is like if we can give isolation of each memory space. And what that means is that like when we are using the program 1, we will use this page table. And then when we switch from running program 1 to program 2, then we will use a different page table. And that means, so that even if we have the same virtual address, 8048,000, and then for the same address 8048,000, and then we will have a different physical address per each table. And then if we switch the table at the CPU, then there is no way for a process access to another table. And then you will see that how it will be implemented in the Intel CPU in this lecture. And we will implement this kind of the virtual memory. So the imaginary table that between the mapping between the virtual address and physical address using a technique called the paging. And how we implement paging is that we logically split. So we just think the physical memory space as a linear address space, but logically separate each memory as in 4 kilobyte block. And then the reason why we choose 4 kilobyte is with the practical reason. And then at the end of this lecture, we will go over why the page size is 4 kilobyte. But you can, at this time, you can just memorize that our page size is 4 kilobyte, and then that's the minimal granularity that our virtual memory system will manage. And then the good thing about like having the page size as a 4 kilobyte is that that's exactly 2 to the 12, 4096, and then makes, if the address is multiplication of that number, then like last 3 digits of the hexadecimal number will always be 0. Yeah. So the first page starts at the address 0, and then second page, the 4096 is exactly 1000 in hexadecimal. So you can regard like the last 3 digit as 0 as like a page aligned address. And then what we will do is we will have an indirect map between the virtual page to physical page. So suppose we have a virtual address, arbitrary virtual address, for example, 81815000. And then you will see that last 3 digits as 0, that's 2 to the 12, like the 12-bit aligned. So last 12 bits are all 0. And then if we map this virtual address to a physical address 32000, then any address in between this page to the next page, for example, from 818150 to 1, 2, 3, 4, and until FFF, that will be translated into the same physical address 32000 from here to FFF. So what that means is that like we will only keep the mapping between one page to another page. So for this example, so if suppose there is a virtual address 80480000, then we will translate this page into physical page 10000. Then what will be the address we will translate if the supplied address is 8048012? Then 10012. Yeah. So that we will translate the virtual page address to the physical page address. And then in that translation at the CPU, we completely ignore the last 3 digits. Yeah. And then although I will describe like the virtual memory as like having this kind of table, but actually how the Intel CPU will translate this table is this kind of with this kind of diagram. So they do not have a linear table simply. So what they do have is like that they do have a 2-level tree-like structure. So you can regard like that, like a CPU only knows the page table address at the CR3 register. So CR3 register is control register number 3, and then we reserve this register to point to the page table address when we enable virtual memory. And then that table is not a single linear table. It is a tree-like structure. And then that points to the page directory, which only has a 1024 entries in here. And then each of the entry will points to the page table. Then like we can get the virtual page address. And then we will revisit this kind of the 2-level architecture again. So please don't worry much about like if you cannot understand why there's a 2-level at this time. Then we will go over the details of how the virtual to physical address translation goes on. So we will use a page as a minimal granularity for the virtual to physical address translation. So the page size is 4 kilobyte. So in the address translation, we will completely ignore the last 3 digits offset, because these offset we will not translate, and then we will just cut off and then add that later. Yeah. And because we are working with the 32-bit computer, and then our virtual memory space entirely is in span over the 2 to the 32 choices, 32-bit cases. But we set the page size as a 2 to the 12. So the number of available pages in the entire address space would be span over like the 20 bits space. So starting from the bit 12 to the bit 31. So we only have 20 bits to indicate the pages. So the number of available pages are 1 mega entry, yeah, to 20. And then we can easily split the page number and the offset from the hexadecimal format of the address. So because the page size is 12 bits, so the last 3 digits are the offset. So whenever you see the address formatted in this kind of the hexadecimal number, then you can easily point the last 3 digits are offset, and then like the upper 5 digits are a page number. And then in x86 32-bit CPU, we use 2-level page tables. So suppose we have like the huge page table for the entire page, then like we need to store like the all 1 mega entries of the virtual to physical address translation, but not all processes are using that much of memory. So to save a little bit of space about having a smaller page table, we use this kind of a tree structure. And then to compose that kind of tree, we split the page address into 2. So we have a 20 bits page number, but we will split the page number into 2. The upper 10 bits as a page directory, so which is like an upper tree index, and then the lower 10 bits as a table index. which is a lower tree index. So we split the 32-bit into 12-bit offset, and then 10 bits for the table index, and 10 bits for the page directory index. And how we use all the address part to the address translation is something like following. So we have a 32-bit virtual address. And then first thing is that like we need to cut off the 12-bit offset at the tail. And then for the upper 20 bits, we split it into two. And then I show you that from CR3 register, we have a page directory and then page table. So it's something like a tree structure. And then how we access the tree is that, so we will use the top 10 bits to index the page directory. So for example, suppose we have an address as a 08048000, then our offset is 30 at the end. So offset is 0. And we get the page number as a 08048. And then these are like the 20-bit numbers. And then if you cut it in a 10 bits by 10 bits, then you will get the number 0x48 for the lower 10 bits, and then 0x20 for the upper 10 bits. And then we use this upper 10 bits 0x20 to index page directory entry. And then this page directory entry stores the physical address of the page table. Then we can refer to the page table, and then we select page table entry with the page table index, which is the lower 10-bit of the page number, and that is 48. Then finally, we can get the physical address as 100000. So, you can conceptually regard the page table as a big table that stores every virtual address and then virtual physical address pair. But we only store that kind of pairs per each page, because how we will translate the offset is something like, suppose one of our mapping is 8048000 to 11000. Then suppose we have the offset, non-zero offset, then just split into two and then translate the page number and then add that at the end. So this is how we translate the virtual to physical address. So we don't need to translate the offset part. We only need to translate the page number. And to matching the page number, what we have is like these kind of the two-level page table to store all the page tables in the page directory. And then in the page directory, we can find that the information about like which physical address the current virtual address is mapping for. So the important thing is like we don't translate the lower 12 bits. So let's take a little bit of example. So suppose we have an address 8048338. Then, so what CPU stores is not this kind of information. So they just store the page numbers. So take off all the, tear off all the last 3 digits, because we will not translate it. Then we only store the virtual page number and then physical page number. And then from the address, by stripping off the last 3 digits, we can get the virtual page number. And then for this virtual page number, we can consult to the page table to get the physical address. But we can split the address with the virtual page number and the offset. And then we can get the corresponding physical page number from the page table. That is 10. And then physical address is that we shift this into the 12 bits to make it as a page address and then add the offset. Then that's how we can translate the virtual address to physical address. And then let's take another example. Suppose we have a virtual address 443325AF. Then we can split the virtual page number and in offset by cutting at last 3 digits. And then we can find 44332 in this table as translated into 33885 as a physical address. And then translate this into the page address, adding 3 digits at the end, and then add the offset, then we can get the physical address for that. Any question about like this translation? Yes?
But what happened to the 64 bit? Is it the same as 32, but it's wider or?
So like so I explained that like the 32-bit machine has a 32-bit address space, and then we will use like a 4 kilobyte page, and then like a 32 minus 12 bits, then we have 20 bits. And then the reason why we split 20 bits into 10 bits is that suppose you have a 1 page that's 4 kilobyte, and then in 32-bit machine, what is the basic pointer size? It's 4 byte. What that means is like that we only have a 32-bit address space. So to point to every single address, we need to have a 32 bits. And then in 4 kilobyte, we can have 1024 entries of the addresses. Yeah, that's why we can only have 2 to the 10 entries. So 10 bits for the page directory, 10 bits for the page table. But when we get to the 64-bit, so suppose we have a, so in 64-bit, we don't use the full 64-bit address space. Right now, we are using 48-bit address space. But think about 1 page size is 12 bits. So that we don't translate 12 bits. 48 minus 12 is 36. So we have 36 bits. But 1 page size is remaining the same, 4 kilobyte. But the address size in 64-bit is, each pointer size should be 8 bytes. So we only have 512 choices. So to make the page directory or meet tree entry to have like a 2 to the 9 to 512. So we can only use 9 bits for the address per each level. So what I mean is, so because the reason why this page directory and then table is like they can address up to 10 bits is that like the in 32-bit pointer size is 4 byte. So 4 kilobyte divided by 4 is like that there will be 1024 entries, and then 10 bits can represent 1024, so that we can consume 10 bits per each level of this kind of tree traverser. But in 64-bit, we have 4 kilobyte page, but if we divide that by 8, then we will have 512 entries, so we can only consume 9 bits. So in 32-bit case, if we subtract 12, then there are 20 bits. So 10 bit, it goes perfectly well. But in 48-bit address space, if we have 12 bits as an offset, then we have a remaining 36 bits. And then in each level of the table, we can consume 9 bits because the pointer size is bigger. And then you can easily calculate 9 multiplied by 4 is 36. So we will have 4 level page table in 64-bit. And then that will also explain why we can have like a 48 address space. And then after that, we will have 57 bits of the address space. So 48 plus 9, because by adding 1 more level on top of 4 level page table, we can have like the 9 more bits to be translated. I believe it could be better understandable with some of the figures, but maybe I can explain that later. Yeah, about that. So the important thing in the virtual address translation is that like the internally, the CPU, when after the paging is turned on, whenever the CPU sees this kind of address, internally it will cut off, offset, and then use the top 10 bits and then lower 10 bits as like the index for the page directory and table. And then automatically translate the virtual address into physical address. And then these are the examples. And then the inside of the page directory and page table. So what page directory does is like the page directory is like the intermediate node that refers to the final where the final table is. So we will use a page directory as an intermediate node to find an actual page table, this one, yeah. But in doing that, we will also make all the page table will be page aligned too. So that means our last 3 digits in hexadecimal numbers for all page numbers are 0. So we will not use these kind of the 12-bit part. And then because that kind of resource is quite scarce, so engineers repurposed those bits into like the storing some important data on it. So take a look at this one, page directory entry. So the page directory is the first tree structure that we will refer to find where the page table is. But in there, we can also store some more information. So take a look at this p bit present. So if that value is 0, that means the current entry is invalid. So suppose you have a page directory and then every entry wiped with 0. And then that means that like even for the present bit will be 0. So even if you have some of the address values upper part or something, then CPU will ignore it completely. So what CPU will regard about that data is like they will regard it as a empty entry. Yeah. And then the writable means that that memory is writable or not. So the reason why it has a writable flag here is that, think about it. So after we turn on the virtual addressing, all the address in the CPU need to be translated with the virtual to physical translation. And then because we mark the memory permission if that is readable or writable at the address translation, then when CPU translate the address, then it will naturally know that that address is writable or not. So if that address is a read-only, but the CPU attempts to apply the write access, then the CPU knows that and then kill the process. So this is how we can implement security over the memory system. So let me explain it in a different way. So because the address translation must be involved in any access of the memory done by CPU, so we will insert some of the security flags, for example, readable, writable, or if that memory is for operating system kernel or like an application, so that we can embed that kind of information in the page table of our page directory entry. And then we will embed all these information in the not using the lower 12 bits of the entry. Yeah. So you can regard like each of like this kind of entry, not just storing the page number, it also stores this kind of the flag. And then to enable paging, so protected mode can be enabled by turning on the PE protection enable bit here. But on the opposite side of in the CR0 register, we have a PG bit. So that's for enabling paging. And then after we enable paging, all the address translation, so we'll refer to the CR3 register. So the CR3 register will store the address of the page directory. So conceptually, how that works is, so after we turn on the paging, then whenever CPU sees the address, it will refer to the CR3 first, and then it will chop the address into 10, 12 bits, and then access page directory with the top 10 bits index. access the page table with the second 10 bits index. And then after getting the physical page number, and just attach the offset at the end. So that's how the translation works. And then before turning on the paging, we need to set the CR3 register value to correctly point at this page directory address. And how we enable that in JAWS is that it's inside a kernel. So when you take a look at the source code of the kernel, that entry.s, then you will see that it will load the entry page directory. So the JAWS will create some fake page directory first before you're starting lab 2. Because in lab 2, you need to construct your own page directory and page table to fully support the virtual memory on JAWS. But before that, it sets some of the dummy page directory for accessing the virtual and physical memory. So how it does is like after loading the page directory address to EAX, and then move that address to CR3. But make sure that right now we are before turning on the page, so all the addresses are physical address up to this point. But after that, so it gets CR3 to EAX, and then enable, protected enable, and paging, and then put that back on. So after running this line, then both protected mode and then paging will be enabled. Yeah. So important thing here is that like if we set the CR3 to point the page directory address, and then we turn on paging by setting the CR0 register. Yeah. Then here will be an interesting question about that. So the important thing here is that after we turn on the paging here, yeah. So if we turn on the CR0 PG as 1, then CPU will regard all the address as a virtual address. Yeah. And what that means is that, so we load the kernel right above the 1 megabyte of address in physical. So our kernel will be in the physical address 100010, that kind of near that address. But the problem is that after we run this instruction, all your address will be virtual. Then, so we previously used this address as a physical address. There's no problem of accessing that because physically our code is there in that address of the DRAM. But the problem is that after we turn on the paging, then our CPU regard that these addresses are virtual. So we need to have a translation for these addresses. So to access the physical memory at all time, after we enable the virtual address, so in JAWS, we intentionally map any address starting from F at the highest bits. So what we are doing is like we reserved starting from F00000 to FFFFFF, and then we directly map all these virtual address into physical address that we removed F at the head. So it's something like we have a virtual address space. We have physical address space. We are playing in the physical address space, but right after running this instruction, all the addresses need to go to translation. But to access the existing physical address, we need to have a direct mapping from the virtual to physical address. And then this mapping will serve as accessing any kind of physical address using the virtual address space. So how it is implemented in the JAWS is that, so the first part, so this is the entry page directory. So the first page directory that the JAWS will use. And then what JAWS is doing is that, so 0 entry. So the first entry of the page directory will be for the address space from like a 0 to 4 megabyte space. And then it will directly map the address into the physical address. So what that means is that for the bootstrap part time in JAWS, so any address from the 0 to 4 megabyte in virtual will be the same as a 0 to 4 megabyte in physical. And then JAWS will do the same thing for the last entry, and then last entry is for like the F000 to F04 something, and then what it does is like it will map the first 4 megabyte of the physical memory into that address too. And then internally, how it implements all the page table is that like it goes over all the page numbers. So to allow all the mappings available, so we need to fill the physical page addresses. So it fills from 0 to 1, 2, 3, 4, and then at the end, so to fill up all 4 megabyte space. And then I told that in the page table entry and then directory entry, we have some of the reserved area of the 12 bytes to store some of the flags. So these flags, PTP means present, PTW means writable. These flags are in there at the end of like the lower part of the 12 bits of the each entry. Any questions up to this point? So you will be much more clear when you get to the lab 2 about like when you go down the tree structure of the page table about this. And then next is about page, and then like let's learn about why page size is decided to be 4 kilobyte. Yeah. So I described the page as like the 4 kilobyte block. Yeah. But let's think about why the page size would be 4 kilobyte. And then in 32-bit computer, we can point anywhere in the 4 gigabyte of the memory space, which can be pointed by 32-bit integer. Yeah. And suppose our page size is 1 gigabyte, 2 to the 30. Then we will have 4 entries, right? So our page table need to have just four entries. And then per each entry, we need to point a virtual address to a physical address. So each entry will have a 32-bit pointer. So 4 entries, 4 bytes, then we will have 16 bytes page table. Very small and simple. That would be good. Yeah. So we are thinking about like how big our page table size is to map the entire 4 gigabyte of memory. So if our page is 1 gigabyte, then we need 4 pages, 16 bytes. But suppose we have a 4 megabyte page. Then in 4 gigabyte space, we could have a 1024 entries. And if we have a 4 byte pointer, then to store everything, then it requires a 4 kilobyte. And then if we have 4 kilobyte page, then we would have like a 2 to the 20 entries. Then we need to have 4 megabyte to store entire virtual to physical memory map. But let's go further. If a block size is 1 byte, then we need to translate each byte address to another byte address, and to translate entire 4 like the gigabyte space, we need to have like 4 giga entries. Actually, we need to have 16 gigabyte of the page table. So the last one is a somewhat ridiculous setup, because suppose we are setting up the 4 gigabyte virtual address space. And to do that, we need to use a 16 gigabyte of physical memory. So that's quite ridiculous and then silly construction. Nobody wants to use it like that, right? But what this diagram or what this the listing shows that, so if we have a bigger page size, then our page table size is quite small. So 4 megabyte page, then 4 kilobyte page table. But if we have a smaller page size, then our page table size would be bigger. Yeah. So that's the one matter of the factor that, because per each process you run on the operating system, we will give a separate virtual address space. That means like per each process, we need to have this kind of data structure. So this will be overhead for like each process. As the number of process running on your operating system goes up, then these kind of the memory usage, additional memory usage will be needed. Yeah. So this is the one factor, but there could be another factor that determines the page size. So with this factor, bigger page size looks good for making the page table size smaller. But there's another factor that memory paging also creates a memory fragmentation. So suppose you want to store just 1 byte. Then if you have a 1 gigabyte page, so that in paging, the page is the minimal granularity of the memory. So even if you want to store 1 byte, you need to create 1 page to store that. That means if you have a 1 gigabyte page, then you will waste 1 gigabyte minus 1 byte. And then if you have a 4 megabyte, then your minimal allocation granularity will be 4 megabyte. So you will waste the rest of the memory. 4 kilobyte, then 4 kilobyte minus 1. And then 1 byte, then there's no waste of memory. So the another design consideration could be the having a bigger page size will make you suffer a memory fragmentation a lot. Yeah, because if you want to store many smaller fragmented data, then that means that you need to allocate a bigger space and waste a lot. So there is a trade-off between the page table size and then fragmentation between the page table size, page size. So like so there was a lot of debate between like how we set the page size correctly for the certain purpose, but for storing a lot of the small data, yeah, we need to keep the page size smaller. So in like 1985, the engineers designed to have like a 4 kilobyte page for at that time, but recently it has been changed. Although most of your operating systems still running with the 4 kilobyte page, and they do have options like turning on the 2 mega page and also 1 gigabyte of page, yeah, based on like the purpose of like the system. So for example, if you are running the database with the big chunk of the data are queried a lot, then the better to use like the big page size, because there's a low chance that your page size will be wasted, because most of your data, if most of your data is bigger than a certain page size. So it depends on the options, but in general engineering, so still the 4 kilobyte page is good in terms of the size of the page table, because even if we fully fetch all the fully map all the virtual to physical address, we only need 4 megabyte of the space, which is less than 1% of the total address space. So that's a good engineering choice. And then let's do the little bit of recap about like how the address translation worked. So whenever we have a virtual address like this, then we can split into 2, offset and the page number, and then just ignore the offset for now, and then split the page number into 2. And then CPU will first query the CR3 register, find the page directory, and then index page directory with the directory index, which is top 10 bits. And then next, it will find the page table, and then access on the page table with the page table index. Then we can finally get the physical page number. And then we can get the offset at the end, then we can have the memory access. So now the changes happens in the CPU side is that, so suppose you want to read data on this address. So we want to make a one read access, but that actually turned into, we need to access page directory first, page table for that later, and then actual memory access happens at here. So what that means is that, so after enabling paging, suppose we have this kind of an instruction. So what this instruction do is load the 4-byte data from this address to EAX. So it only involves one memory access, but due to page table lookup, we need to look up page directory and page table. That kind of lookup will add 2 additional memory accesses. And then another interesting point here is that the CPUs are very fast. So CPU runs several gigahertz of the cycles, and then this kind of the move instruction. This is a very simple instruction, just moving the one value to the other from in the register or something. So that takes just 1 cycle. So what that means is that, like, if you have a 4 gigahertz CPU, then this kind of the move instruction can run 44 billion times in a second. Yeah. So the move instruction is so fast, but the problem is that whenever CPU attempts to access data from memory, they need to wait, because DRAM is dynamic. They need capacitors to be charged or discharged to transmit the data. So accessing DRAM usually takes like the 200 cycles. So it's about the several nanoseconds, 50 to 70 nanoseconds to get the data. Yeah. So in terms of like CPU's viewpoint, RAM is very slow. Yeah, that's the problem. So when we are using virtual memory, so we want to give the full flexibility to the process to have a transparency, efficiency, and protection, that kind of goals. But if giving that kind of property requires 2 additional memory access, slowing down the operations. So if we just need 1 memory access and 1 move, then that could be 201 cycles required for the access. But after turning on the virtual memory, we need to have 2 additional memory access. So that could be 601 cycles. So that means every single memory operations could be 3 times slower when we turn on the virtual memory. So in that case, nobody wants to use this because it could be too slow. But to enable the virtual memory and not to lose that kind of the performance, not to lose performance due to this kind of the overhead. So CPU designers try to cache the address translation. And then that cache memory is called a TLB, translation look-aside buffer. So conceptually, what it does is like it caches the recent translations and then reuse that and then keep that in CPU to not access the DRAM again and again. Yeah. And then how the TLB works is that, so whenever we translate one of the virtual page number to the physical page number, we cache it into the CPU and then do not access the memory for the next translation, if that is valid. So the reason why it has a valid bit here is that, so think about like we switch from program 1 to program 2. So if we switch the execution, then all the virtual address need to be invalidated, because virtual address of the program 1 could be totally different with the virtual address of the program 2. That's why we have a valid bit at here. And then let's take a look at how the CPU will work with the virtual to physical address translation if they do not have TLB. So suppose we supply this address. Then it first consults to CR3 register to get the first page directory entry, and then access that with the index here, and then get the page table address, and then access the entry with the index in the address. Yeah, and then we can get the physical address, and then offset is 000. Then access the memory. So we will have 1, 2, and 3 memory accesses to have one memory access in the CPU. But suppose we have a TLB, and then the result is cached in here. In that case, it directly goes to the TLB, and then 1, 2, 3, 4, 5. Then will be mapped to the 10000, and then we will directly get the address. And then this kind of access, because this TLB is in the cache memory, it's not a DRAM, it's a so-called SRAM, and then its speed is so fast. So we don't have to wait around the 200 cycles for the memory access, but directly access the physical address. Then we can have only one memory access for delay for it. Yeah. So the good thing about having TLB is that like we can cache it, and like we don't have to go through the translation. Yes.
So where do we store it here?
So TLB is inside the CPU. So the CPU reserved a certain memory for it. So I believe it's inside of the L1 cache, and its size is around 8 kilobytes in modern CPUs. So how the translation works with the TLB is as follows. So suppose we supplied an address, and then it first try to access the TLB, and then our page number is 1, 2, 3, 4, 5, and then that is in the TLB, and then that's valid. Then it's hit. Then we can translate the address. So the address translation result is 678 because the PPN is 0, and then offset is 678. But suppose we have a different address, 1, 2, 3, 4, 9, and then that entry is not existing in here. In that case, it will also access TLB first, and then because there's no entry in TLB, it goes down to the page directory and page table, and then before move on, it will cache in the TLB entry, translation entry, yeah, and then generate the translated address. So later, the same address comes in, it goes to the short path, hit the TLB, and then get the result. But if there's no result in here, then it must go down to the page table work. And then the TLB makes the translation faster. And then so let's take a look at how the modern processors are implemented TLB. So you can search for the CPU information if you search for the CPU code name or whatever. And then I searched for the Core i7 6700K, which is a quite old CPU. And then it has a L1 TLB as a 64 items. L2 TLB as like this amount of items. So that each item will have like the 8 byte of the data, because this is a 64-bit CPU. So you can see that like 64 items, 4-way, and then 8 byte, then you will see that this entire structure is around 2 kilobyte or something. Yeah. And then its miss penalty is 9 cycles. What that means, like if the L1 TLB misses, then it will fetch the data from the level 2 TLB, and then that cycle is 9 cycles. But miss penalty for if we could go to the memory, is around the 200 something. Yeah. And then if we hit on the TLB, then its latency is 4. So in the 4 gigahertz CPU, that's just 1 nanosecond. Yeah. And then let's think about like how the TLB page table works. And then like from the memory latencies, I can get all the information here. And then if everything is uncached, then we will suffer TLB miss penalty 9 cycle. And then we will go over the RAM latency. And then we need to do that for 2 times because we need to go for the page directory first and then page entry. And then that will be resulting in the 124 nanosecond. But if everything is cached in L1, then it will took like just 4 nanoseconds. So if we just directly compare 124 nanosecond to the 4 nanosecond, yeah, then like having a TLB speed up the address translation a lot. And then like even if we have that kind of the page table or kind of structure that involves a lot of memory access and translation, we can speed up by having this kind of cache structure. Yeah. But the problem is that we have limited entries in TLB. So for this kind of the scarce resource, CPU internally implemented like what will be the recently used entry. So they have a priority on keeping that entry for a long time, and then like try to withdraw the evict entries that is not frequently used and also historically. So CPU also profiles like how the memory access patterns goes on for the program, and then they determine like what will be likely be used more in the future, and then like try to evict something that does not have likelihood for the hit rate in the TLB. And then like because TLB structure is scarce, and then there could be some replacement policy. So one of the easy way to implement that is so-called least recently used. So the mark whenever the block is accessed, and then try to evict like the one that has the oldest timestamp that got replaced by the other entry. Yeah. And then like that does not always guarantee the best performance. So there's some of the systems, not the Intel processor, some of the processors just implemented like a completely random scheduler for the TLB evict, but sometimes that works better than least recently used. Yeah. And then we will learn more about this kind of the scheduling algorithms later, because this kind of scheduling also affects on like when we schedule the multiple processes to run all together on the operating systems. And the TLB is just a cache. Then there is a problem that the TLB and then page table entry when they could be the mismatched. Yeah. So that problem happens because like the CPU don't know how the operating system manages the page table structure. So the operating system can freely change all the entries in there, and then like the CPU do not know that like whether that value is changed or not. So let's see how the TLB and then the page table mismatch can happen. So for example, so we have this address 12349.678, but in the TLB, it will be translated into the physical page 101. But in the page table, that's the same. But suppose we update this page table entry. Then this address needs to be translated to 102.678, not 101. In that case, we need to invalidate the TLB entry in the CPU. Otherwise, the address will go to the TLB first, and then it will access the previous data. Then the CR3 register. And then another case that we need to flush the TLB is that, so suppose the address, this one, is valid for these 2 page table and directory and table. And then suppose there is a context switch. What that means is that like when we run the program 1, suppose we switch the execution from program 1 to program 2. then it will have totally different page directory and table. So in that case, we need to flush all entries to load the page table entry from the newly available processes. And we can do this for invalidating this kind of the TLB entry by running an instruction called the INVA-PG. Yeah. So it accepts the memory address as an argument, and then it invalidates the TLB entry for that specific address. So in JAWS Lab 2, you will build the page table and directory structure, and then the CPU will automatically cache your translation result. So whenever you update the page table, you will be required to call this function TLB invalidate for a specific virtual address. And what it does is actually the running invalidate page for that address. So please memorize that whenever you update the page table entry, you need to invalidate TLD entry because these are not synchronized. But the CPU will automatically cache it. So whenever you update it, then you need to invalidate it. And in the slide, I put some of the useful macros that you can use. So pgnum macro in JAWS, what it does is like we only take the top 20 bits as a page number. So it just shipped the page number for 12 bits so that we can take the top 20 bits. And then PDX is like it gets the top 10 bits as an index. And then PTX is like getting the middle 10 bits as a page table index. And then you can use these kind of macros to get the page number, page directory index, and page table index. And then to get the page offset, you can use PG off to get the last 3 digits, the last 12 bits from the address. And then another useful one is like you can get the address part only as a PTE ADDR, and then you will get the so in the page table entry, the last 12 bits will store some of the flag kind of thing. So PTE ADDR, what it does is like it will zero out all the last 12 bits because we don't need that. And then what we actually need is like we need the PTE ADDR of the PTE. So the last 12 bits as a 0, and then add the offset at the end. Then that's how we can calculate the address. And then conceptually, how you can get the page table entry is you access the CR3 register value that points to the page directory, and then use page directory index to get the address of the page table, and then use the page table index to get the page table entry. Yeah. So to do this kind of thing, so you cannot directly use this code, but conceptually you are regarding CR3 register as a page directory table, and then index that to get the page table, and then index page table to get the entry. Yeah. And then at the end, get the page physical address, and then add the offset at the end. And last part is about the summarization of the segmentation and paging. So we learned about the segmentation in protected mode. So the good thing about the segmentation is that the segmentation implementation is not that complex. So real mode segmentation, if we implement that as a logic, then we just need a multiplier, multiply by 16, and then add offset. That's it. But for the protected mode one, so we need to implement the hardware to refer to some of the 8-byte structure, but it has a base and limit address in fixed location. So what we need is like the logic, hardware logic, just compare the base and limit, that's it. Yeah. So the good thing about the segmentation is it's easy to implement. And then like it only requires 8-byte per each region. So in contrast, in paging, we have seen that we need a 4 megabyte of the page table if we fully map the all 32-bit region. Yeah. So that's the contrasting part. So we only need 8-byte structure to manage local 1 segment of the memory. And then we can allocate anywhere in the limit. Yeah, and then we can set the limit by 4 kilobyte granularity or byte granularity, depending on the size. And we can also set the data privilege level, whether the memory is for the privilege 3 or privilege 0. So we can use this kind of the ring model. But the problem of the segmentation is that like it cannot avoid fragmentation. So what that means is like we can set the base and limit, not about like the splitting base the memory space into the multiple pieces. So we need to have one contiguous space available for the entire segmentation. And that means like we could have this kind of the fragmentation problem, because we can only allocate the memory like contiguous like that. And then even if we have a free memory in between, then we could not fit like a bigger memory chunk. But we learned about paging today. So the good thing about the paging is like we will split the memory into 4 kilobyte blocks. So there's no fragmentation for the size more than 4 kilobyte. So for the 1 byte, 10 bytes, yeah, we definitely have a fragmentation within the page size, but we will ignore that because in the most of cases, we will use a lot of data structure which is more than 4 kilobyte. Yeah, and then the good thing about paging is that like the virtual addressing that we will implement, yeah, that does not require a virtually contiguous space. Need to be physically contiguous. It could be separated arbitrarily, and then what it sets is like the virtual to physical page. These are like having the direct mapping, but other than that, there's no requirement for the allocation. So that makes a fast allocation enabled. So we don't need to search for the big contiguous space. Just get the free physical page and then map it, free physical page, map it, and that's it. But the page table also has a little bit of drawbacks. So like it could have internal fragmentation. So if we store 1 byte or 10 bytes, then we will waste the 4 kilobyte minus 10 bytes kind of thing. But in the most of cases, we will use a bigger memory than 4 kilobyte in most of the programs. So it does not matter at all, matter much. And then another problem is like that we need to store this page directory and table structure. But at the worst case, it will be 4 megabyte for full memory usage. So think about it. If you use 4 gigabyte, then we will use 4 megabyte as a managing structure. So it's less than 1%. So it could be somewhat reasonable to having like that kind of the structure size. And then page table lookup could be slow because it will incur 2 additional memory accesses, but we can speed up with the cache structure like a TLB. Yeah. And then we learned about the address translation. So segmentation was like a base address plus offset, but that need to be smaller than the limit. But the address translation in paging is that we will change a virtual page to the physical page, and then we will add the offset. And then please go over the pros and cons of the segmentation and paging. And also like another important part is that the paging requires 2 additional memory access in translation. And then we can speed up that with TLB. And then please do the recap about like how TLB works with the animation at home by replaying the slides. Thank you for your attention. And then this is the end of the lecture, today's lecture. And then feel free to ask any questions.